Hello everyone, welcome to this online probability series. Today I want to tell you about passage times for partially homogeneous reflected random walks on the quadrant. So that's a mouthful. Let's start with some intuition to get the ideas going. Consider a simple symmetric random walk on Z2 and take the absolute value of each entry so that what we have is a process confined on the quadrant, on the positive quadrant, as represented here. We also see in this image that we have a perfect circle in the interior, and this is to represent the covariance of the increment at the interior. At the interior there is no drift, but at the boundary we have some drifts. For instance, let's look at this horizontal case, this horizontal point. If we jump to the right and left with equal probability 1/4, but now here we jump up with probability 1/2. 1/4 for going up directly and 1/4 if we go down and take the absolute value so that the reflection is acted upon the walk. So this process, we are interested in studying the return times for this process, and this in this example is very classical. We know it is recurrent. Not only that, we know it is critically recurrent in the sense that if we take any positive value s, the expected value of tau raised to the power s is infinity. Okay, so this image here is meant to represent not only the simple symmetric random walk, but a class of homogeneous walks on the quadrant, and that's what we're going to see in a moment. But let's allow instead that the way we jump to the right or left at the boundary is not with zero drift. We allow that we jump, for instance, with higher probability to the right than to the left at the horizontal boundary. So this gives us a positive drift of moving away from the origin, as we can see here in this direction. So since the previous walk was already critically recurrent, it's reasonable to expect that in this case the walk will become transient. And we can say, and we can prove that. We can say that this walk is transient. If we do the other way around, if we jump more towards the origin at the boundary, giving us a drift that is confining the process in balls around the origin, then the process becomes recurrent, and not only that, we start to get some moments of return times. We'll find a quantity chi, positive, strictly positive, for which expected value of tau 0, is less than infinity for raised to the power s is less than infinity for every s less than chi, and for every s larger than chi, this expected value will be infinite. Okay, so we're quantifying the recurrence of this walk with this number chi. Very good. Now we can start playing with these quantities, with the drifts. Instead of making all of them point towards the origin, we can have one pointing towards the origin, the horizontal one, and the vertical one is pointing away from the origin. So we have contradicting pushes for the process. One pushing towards the origin, the other pushing away from the origin. In this case, we're not able to say if it's recurrent or transient without more information. We'll need to measure we need to know specifics about the direction of this drift to be able to classify the walk. Another interesting case about these homogeneous walks on the quadrant is if we change the covariance matrix of the increment at the interior. So instead of jumping uniformly to a point on the circle, roughly speaking, imagine now we are jumping with some covariance. For instance, here a positive covariance, here on the left a positive covariance, and here on the right a negative covariance. Okay, positive correlation, negative correlation. Okay, so which one of those is recurrent, the other one is transient? Which one? So the first time I saw this question, I thought that the right one would be the recurrent, because the left one seems to be due to this the direction of the ellipse is kind of, if we see this as an arrow, it's pointing away from the origin. But in fact, that's not the case. Having a positive correlation makes the walk be more one-dimensional, and being more one-dimensional, it is more recurrent. And in the other case, the one that is negatively correlated, the one on the right, the walk never gets lost, becomes transient, and never meets the origin again due to it being circling around. It gets lost and is transient. Okay, so now we can start changing not only the covariance matrix, but the drifts. So we have three quantities to play with: the drift at the horizontal boundary, the drift at the vertical boundary, and the covariance matrix at the interior. And we would like to be able to say when the process is recurrent, when the process is transient. And there's an answer to that. The answer is the following. If we're giving this picture with a covariance matrix sigma and angles θ1 and θ2, just to be clear, θ1 here is negative. The way we measure is positive if it points towards the origin and negative if it points away. So θ1 here is negative and θ2 here is positive. So if we're given the angles of the drifts and the covariance matrix, we are able to find a linear transformation T sigma here, that makes the covariance matrix become an identity, following the formula here that's written out: T sigma times T sigma transpose equals to the identity. So, and as you can see, what we're doing is we're keeping the horizontal line fixed, and the vertical line we're pushing it away, opening up the quadrant, turning it into a wedge with angle phi 0 at the apex here, as we can see represented. It's interesting to see also that θ1, sorry, that was negative, now is mapped to a drift that has angle phi 1, and this phi 1 is positive. So this is really the angle that we want to look at: phi 1 and phi 2 and phi 0. We take these three informations, compute chi as the fraction of phi 1 and plus phi 2 over phi 0, and we're able to do the classification as follows. If chi 0 is negative, the process is transient. And if chi 0 is positive, the process is recurrent, and we can say something about the tail of the return times. And that will allow us to say how many moments we have. Okay, so this is the starting point for us. This is just intuition. I know some things have been somehow informal, but we'll begin now. The point is that for homogeneous walks on the quadrant, there is a way of classifying recurrence and saying how many moments we have for such processes. Okay, so now let's begin properly with our talk. It is divided into parts. First, an introduction where I want to tell you about the context of the problem and some literature review, state the result that we're going for, and discuss some heuristic general arguments in the classical setup to obtain quantification on the moments of return times that we've been seeing here. And the second part of the talk is to discuss the methods, the concrete methods for the implementation of the proof. So I don't want to go into the details, but I want to discuss the main ideas. Okay, so let's begin. So this project is a joint work with Mikhail Menshikov and Andrew Waite, both from Durham University, and they have been studying random walks, recurrence of random walks in several contexts, from homogeneous walks to non-homogeneous walks, and this one belongs to the class of random walks on the quadrant, which is a topic in itself that has been of interest to us, namely on two emblematic papers. The first one is the one that studied passage times, moments of passage times is a work by Aspandiarov, Yasnogorodsky, and Menshikov from 96. And a second paper that studies these random walks that allow for some rich behavior at the boundary. What we saw before was a simple behavior at the boundary. They extended this to allow some rich behavior at the boundary. This is a paper by Menshikov and Petritis, 2002. And these two works have been the inspiration for our present work. So that's essentially the context, the literature context for us. But to be true to the subject, this goes back to Kingman 61 and Malishev in 70s that started studying recurrence of random walks on the quadrant. And there have been more people contributing to the field. I will not be able to mention everyone in detail. We'll just be focusing on these two works, 96 and 2002. Okay, so what are we talking about? We're considering maximally homogeneous walks in the literature, at least. This paper by 96 considers maximally homogeneous walks on the quadrant. What are they? These are walks that have the same transition law. They are confined to the quadrant, and they have the same transition law on every point of the lattice. So that's only possible if you can only jump to the right or up. But since we want to have zero drift, to have a chance of being recurrent, we're not able to, we need to allow jumps in the negative direction. And so there will be a different behavior at the boundary. So the maximally homogeneous walks, they have the same transition law at the interior, and they have some different behavior at the boundary. But to be homogeneous, we have a further constraint on the transition law that I'm calling here P0. So the transition law will be bounded by -1. We cannot jump -1 on the x direction, less than -1 or less than -1 in the y direction. So we cannot jump more than 1 down and more than 1 to the left, so that we remain confined in the quadrant and have the same transition law on all points of the interior. We also need to put some conditions at the boundary for the reflection, and we want them to be homogeneous along the line, so it will be the same on every point of the line, and it will give us a certain drift that's indicated here by this blue arrow. In gray is the region where the particle can jump due to the constraints in P0. We can only jump to this region here, to the right and up of the gray lines, dashed lines. Okay. So what is it that we want to study? We want to go beyond the restriction of jumping -1, or of jumping at most 1 down or at most 1 to the left. So in our case, we allow for jumps that go more than that in the south or west direction. So to do that, what we split the transition law into 3 types according to 3 regions. One region, which is the region at the interior that I'm calling x0, and in this point x0 we jump from z to z prime according to their difference. That's what's written here, P0 z prime minus z. That's the law, our transition law at the interior region x0. But now we also allow for jumps more than 1 down and 1 to the left. So we have to be careful and change the transition law on a thicker region of our plane. And this is, for instance, region x1, where we are allowing possibly different transition laws according to each line of the process. So let's look at this one. So if I'm at z and I'm jumping to z prime and z is in x1, then my transition law will depend on the second coordinate of z, namely z2. Okay, so we have for each line here, we have a transition law, z1, that depends on z2, right, for each line. So let's count 1, 2, 3, 4, 5. So we have 5 lines we have 5 transition laws just for the horizontal boundary. And the same thing we apply for the vertical boundary x2. But now the transition law will depend on the first coordinate z1. Okay? At the corner, we need to specify the transition law, but this is really not important for us, for the recurrence. We'll focus on what happens away from a bounded set, so we don't need to worry about the corner. So let's not specify that here. But to complete the definition of the process, we need to have a law for the corner, which is something that makes the process work. Okay, confine it in the quadrant and allow it to exit. Now, the point is that we want to see these partially homogeneous walks as somehow belonging to the same class of maximally homogeneous walks, at least for classification. So what we'll do, and I'm giving the answer here for a problem, is we will look from a distance at this quadrant, and whenever we visit the boundary, we'll change time so that the thick boundary becomes a thin homogeneous boundary, and we homogenize the different drifts that are represented here in light blue into a single drift that's represented here in darker blue, a single drift that will be the direction of reflection at the boundary. So this is done with a time change, and the goal is to then get the same information of angles and be able to classify the walk according to the angles and the covariance matrix, the angles of the drift at the boundary and the covariance matrix. So this is our case, partially homogeneous walks. So let's state our result a bit more formally. We start defining the regions where our process lives, x0, x1, and x2, just like in the previous picture, and more formally written here in terms of these sets IR and IR bar, one the complement of the other in Z. And we have these 3 transition laws that must satisfy some properties. First, to remain confined in Z2, the process satisfies boundedness on the jump, left and down, as you can see here in this remark. And we also assume that the process as a whole is irreducible, that can be decomposed into these 3 in this homogeneous condition. This is the partial homogeneous condition. This is what's encompassed by condition 1 here. So we assume irreducibility 1. We assume that the moments, the transition kernels, have bounded moments, first and second moments, in order to be able to compute increments in the Taylor expansion and compute recurrence as a function of the drifts or the covariance. So we have this bounded moments assumption. Another assumption that's to be interesting for us, we want this P0 law to have 0 drift. That's what we're saying here by 0 interior drift. And we want P0 to have a positive definite covariance matrix so as to have a non-degenerate transition law at the interior. Okay, so given those assumptions, we can state our theorem, which will be vaguely stated, but even though it's good to state it right away, just to get the ideas of what we're going for. If we have a random walk that satisfies the condition stated above, condition star, then there will be a quantity chi, which is chi of z, the random walk z. We have chi that has a formula that can be written below, but I don't want to write it right away, such that if chi is less than 0, the process is transient. And if chi is positive, strictly positive, then it will be recurrent. And these are the moments of return times that we have. For every s less than chi over 2, expected value of tau to the s is finite. And for every s larger than chi over 2, this will be infinite. So chi over 2 is the critical point for the amount, is how recurrent our process is. So it can be kind of off-putting. Why do we have this over 2 on this chi over 2 thing appearing? This should be clear in a moment because I want to discuss how we obtain this classification, what is the heuristics for that, and you see the factor over 2 appearing very naturally in our computations. So, okay, so how do we get bounds on the moments of passage times? How do we get those? How do we get this control in the theorem? Well, we combine an upper bound and a lower bound. So these bounds are obtained with super-martingale's or sub-martingale's reasonings. So let's start with the upper bound. We consider a process xn with n and n. I'm just calling this x. That when we raise it to the power 2p, it is a positive super-martingale. So assume we have a positive super-martingale x to the power 2p. Not only that, assume that we have a rate of decay for this increments. So a super-martingale wants to go down in mean. And in our case, we're assuming that it wants to go down at least by a factor away from the origin. So I am allowing x to be larger than a. So if I have this away from the origin, a rate of decay of xn, of the increment of xn raised to the power 2p, as is written here, then we are in good shape to study the return times to the region A, for instance. First thing we note is that un, given by this formula, is a super-martingale, and this is not trivial. It involves some inequality, some computation, and the use of this hypothesis, but it's the core thing that we need to continue on to get some estimates on the return times. So we prove that un is a super-martingale, and having that, we can obtain the following bounds that I hope you can follow here with me. First bound here, first inequality, is coming from the positivity of x squared. So it's very simple. It's just using the positivity of x squared. So, and the definition of un, really. So now for the second inequality, we use that un is a super-martingale, meaning that the expected value at the time n is less than the expected value at time 0. And the final equality is just the definition of un and the fact that we're taking x0 to be a deterministic value. Okay, so now we can take n to infinity and conclude that the expected value of tau a raised to the power p is less than a constant that's a uniform constant here. So it would be for any n, but then we take n to infinity and get this uniform bound on all. We get the bound for tau a. Clear. So to get an upper bound on the tail of the return times tau a, we use a Markov inequality. So look here, we started with a 2p positive super-martingale, and we got an upper bound on the tail of tau a of a factor n to the minus p. So this is a polynomial decay here. And to get a full control of this, or a better control of this, of the tails of these return times, we are looking at, we will need to find a lower bound. And the lower bound is done with the help of a sub-martingale. So now assume that x to the power 2p is a sub-martingale. At this point, you should be asking yourselves, wait a second, Conrado, you had a positive super-martingale in the previous slide, x to the 2p, and now x to the 2p, you want it to be a sub-martingale. So what you're really going for is a martingale. And I will say, no, I'm going for something that is almost a martingale. So I will not necessarily use the power 2p, but I will use 2p plus epsilon and 2p minus epsilon to get the control on the tail. So they will be off by an epsilon in the decay rate. So they will not be very sharp, but that's what's possible to do with the approximations that we need in the process. So, right. This is what we call almost martingale. So we're looking for almost martingale. So it's not an x to the 2p is a martingale, but it's almost a martingale. Or for our case here, we can forget about the previous slide and just focus on x to the 2p and assume it's a positive submartingale. So being a submartingale, we can now consider the first moment that we go, ooh, this is a typo here, above A. The first moment that we go above A, so sigma A, is the first moment that we go above the level A. So apologies for the typo here. And what we're looking here is that if we use this optional stopping theorem, we have a bound being a submartingale on the expected value of tau 0 minimum sigma A of the process stopped at tau 0 minimum sigma A, the first time that we go below 0 or above A. So look at this process here, x2p. So first inequality is there. The second approximation here, a bit of a hand waving, is using the fact that the overshoot on the level A is not very large. It's comparable to A. So we either go below 0, in which case, or at 0, in which case we have no contribution for the expectation, or we go above A, in which case we have a contribution of a to the power 2p, of order a to the power 2p. So this is really what we are looking for. And if we combine these two, we get a lower bound on the probability of going up of A before going down to 0. So this is what I'm calling the up condition. And I want to combine that with another condition for the process, which is if the increment satisfy these two bounds, the one on the xn squared and xn to the 2r, for r larger than 1. These are rather technical. I don't want you to get desperate and focus too much on that, but let's just accept that it's a bit of a work here, that if we have these conditions, then we are able to find epsilon and delta such that we can spend a long time away from the origin if we start from A. And it's of order, you see, if we start from A, we spend A squared with probability time away from the origin with probability at least 1/2. So I'm calling this condition the condition away. I'm staying a long time away from the origin. Right. So to get a lower bound on the return times, we need to combine these two conditions. So we take A to be proportional to x, and then we ask, or square root of x, I'm sorry, and then we ask the probability of starting from 1 that I do not visit 0 before x seconds, or before x, so tau 0 larger than x. This is what I'm asking here. So this will be larger than the probability of meeting the two conditions of going up and away, and up is sigma A less than tau 0, and away is the condition here that gives us the contribution of 1/2. So you see, because x, we're taking here A proportional to x to the 1/2, we have a factor x to the p from the up condition, right? There's a constant as well appearing, and there should be, we shouldn't really worry too much about the epsilon. It could be hidden as a constant, and there would be more constants appearing because of the 1 plus delta factor. So the point is now that we have a lower bound on the return time, tau 0 being larger than x, and is matching this value here, p. So if we have 2p as submartingale, we have a lower bound of order constant over x to the p. And that's how we combine upper and lower bounds to get sharp control on the tail of tau 0 or tau a for any value a, and get control on the return time, on the moments of the return time. Okay, so this concludes the first part, and now we're going to discuss what do we need to do to treat the partially homogeneous walks. All that was said in the heuristics part, this has been formally written and developed in that paper by 96 of 96 by Aspandiarov, Yasnogorodsky, and Menchikov. So we're just exposing their ideas. There's nothing new. But now, in our case, we want to be able to deal with a broader class of models and understand the case where boundaries allow for rich behavior in the same framework of random walks that allow for more than one jump down or to the left. So that led us to the definition of those regions. We have these thick boundaries, and the way that we want to understand these partially homogeneous walks as maximally homogeneous walks, or almost the same techniques with using the same ideas for maximally homogeneous walks, is that we'll make a time change, and we'll hope to get, we'll prove that we get an homogeneous behavior for the drift at the boundary, and this is what we call stabilization. So to explain the stabilization step, what we're doing here, we are allowing an increment for any point at the boundary. So z here is a point in x1 or x2. So I should have written here z in x1 or x2. We allow n to be a natural number. We're taking the drift around the increment of n steps around z, and we're normalizing that by the number of visits we have at the boundary. So the key proposition for us is that there will be vectors mu1 and mu2 that will capture the asymptotic direction of the drifts. We'll never know if we're matching them for sure, if we're exactly at this direction, but we can be of order epsilon close to it. So this is what we call the stabilization. So just to be clear with what's written here in line 3, is we're taking a point z in the boundary x1 or x2, so k is either 1 or 2, and we're taking it very far away from the origin, at least 2rn away from the origin in absolute value, so that on the first n increments, we are sure never to visit another boundary than the boundary that we started in. For instance, if we started on the horizontal boundary and we start very far away from the origin, due to the boundedness of jumps being r, we only visit boundary 1. So we will get a drift from every visit, and we'll normalize this by the number of visits. This is the formula for the nk. And after this normalization, what we have is that we are approaching, if n is sufficiently large, an asymptotic direction, mu1, if we started from the horizontal boundary x1. Okay, and the key to prove this result is the ratio ergodic lemma that says that if we start with a recurrent Markov chain and we count the fraction of visits to a point of this chain to a region, so let u be a point in IR, the fraction of visits to u with respect to the visits to IR, the region, remember this was 0, 1 until r minus 1, will be an invariant measure by u, will be a value. Exactly, it's just a convergence of the relative frequency of visits to the points. We're not saying here that pi is an invariant measure, but it is the invariant measure. This is what the ratio ergodic lemma gives us. Good. So in images, what's happening for us in stabilization is we have a point in the boundary. What we do is we make a time change. If the point is at the interior, we just have an increment of size 1 for the process. And if it's at the boundary, then we allow it to jump by a factor big N. So this is a time change. And now we want to look at the increments Zn minus Z for Z at the boundary. And we will write this as a sum, telescopic sum of the increments of consecutive plus 1 increments. So sum over L from 0 to n minus 1, expected value of ZL plus 1 minus ZL. And then we decompose the sum over all the possible values for ZL. And using the Markov property, we have that this will be a drift mu1 that depends only on y, which is the horizontal line. I'm taking here the example that z is in x1, okay, the boundary, the horizontal boundary. So that what will be really summing in the end is the local time, expected value of the local time of the process y at the lines little y in IR. So this is the formula for the expected value of the increment z over a gap of time n. And then we bring the ratio ergodic lemma into action to get a convergence for the fraction. So we get a limiting drift for each point on the boundary. Here, boundary 1. So this value here, pi u, is a value that depends on the boundary that we're in. We have pi 1 and pi 2. So here should be pi k in the example here of the ratio ergodic lemma. And okay, so this is what stabilization, how stabilization works for us. And now I want to tell you about the general ideas that we use to complete the classification of this walk, and that's what we call the Foster-Lyapunov methods. So we start with harmonic functions, a class of harmonic functions that will be useful for us to classify these random walks. And these were studied before by Burkholder and Paradan and Williams. They have been studying this to classify Brownian motions on the wedge. So this is the type of harmonic functions that we're looking at. We take in polar coordinates. What we're really doing is that we're raising to the power beta, where beta is given by this formula, beta 1 plus beta 2 over phi 0. What we're doing is we are raising, if you look at in polar coordinates, is of order z to the power beta, the absolute value of z to the power beta. But in complex coordinates is what you do is, well, polar coordinates as well, you rotate this by a factor of beta times the angle we're in. Apologies. And we subtract beta 1 in the angle. This is a rotation of this operation here of taking z to the power beta. Okay, so this is the harmonic functions that we'll be looking at, and what's important for us is what is its gradient, its derivatives, because they will enter in the study of the Taylor expansion. So derivatives of these harmonic functions are written here, and it's good to see how the gradient looks like at the region of interest. So let's say we have a wedge here, phi 0 is the angle at the apex. I'm representing the gradient at point z1, and it's important just to simplify our lives that this is rotated by beta 1 from the vector that defines the boundary, so from the direction E1, right? And the same thing happens at the other boundary, but it's not change. The angle is B2. So we can see beta 1 and beta 2 as the parameters that regulate the angle of the gradient at the boundaries. And they'll be important for us because the angle of the gradient will look at the drift at the boundary and tell us the sign of the increment. Okay, so this is the key. We want to know the angle of the gradient at the boundary. All right. So once we have this idea in mind, how do we examine the increments of these harmonic functions? For our process, we do a Taylor expansion up to order 2. And here's the formula. There's a remainder of order that's negligible for us. We have a first order increment, which is the first term here. And the other two appear due to the chain rule on the fact that we're raising it to the power alpha. This alpha will be important in a moment, but if we take alpha equals 1, we just have the first two terms, right? And then h here, this capital H, is the Hessian of the function h. Okay, so now let's specify to our case where we have a drift that is the transformed drift of the original process by the linear transformation T sigma. So recall that the transformation T sigma is such that, well, the expected value of the covariance matrix is an identity matrix, and due to the linearity is still zero drift at the interior, right? So if we look at the increments, expected value of the Hessian of this increment, we can use this nice property of the trace. Well, the trace is a linear operator. This was a number, so the trace of a number is the number itself. So we can put the trace inside here. And then the trace of matrix ABC is the trace, we can shift, is the trace of the matrix CAB. So I am able to pass this delta tilde here to the other side on like a loop. And then using the fact that this is a deterministic object, take it out of the expectation and use the fact that this expectation of the delta tilde transpose, this is an identity matrix, to say that we're really looking at the trace of the Hessian of a harmonic function. And this is 0 because the function is a harmonic. Good. So the second term here in expected value for us is gone. We just need to worry about the first term and the second term, or in the third term, the first term and the third term. But again, the expected value of the increment dz here for us being delta, the expected value here will go away at the interior. This is a 0. So we just have the third term at the interior, okay? And a negligible term. So because this thing here is squared, we know the sign of this object just by looking at the value alpha. Is alpha larger than 1 or less than 1? If it's larger than 1, this is positive. If it's less than 1, this is negative. And this is how we'll control if it is a super or a sub-martingale, at least when it comes to checking this condition at the interior. We also need to check it at the boundary, which then will depend on how the angle beta interacts with the angle of the drift. If they are pointing, if the angle between them is less or more than 90 degrees. So let's see this in the scheme. If that is at the interior, like I was saying, we only have a relevant increment given by the third term of our Taylor expansion. This is what's written here. And at the boundary, we'll use the stabilization to get a limiting direction for the drift. The increment for the process now has this gap of size n whenever it visits the origin, as a time compression. So it will be given by the sine of beta k, a parameter for our function h, and phi k, which is the angle that the drift makes with the normal at the boundary, right? So sine beta k minus phi k will be what will determine if this increment is positive or negative. The stabilization will tell us that we can control uniformly. This is what we're saying. This epsilon here does not matter too much. We control everything in terms of the sine of beta k minus phi k. Okay, so to get us, just to recapitulate the idea, it's good to see these harmonic functions and their level sets to understand what will happen for our process. So let's take one example here, a couple of images. In red here, we have the direction of the drift is the same in all cases. We have 3 cases here, and what we're changing here are the parameters beta. Okay, we are free to choose our test function, and we want to get as much information as possible from these test functions and get the bounds on the moments of return times. So for positive drift, for fixed drifts direction here in red, we first have beta 1 negative and beta 2 negative. As you can see, it's pointing not in the interior of the wedge, but away in the other direction here. This in black here is the gradient of our functions, is the direction of the gradient of our function h. So what we can do is that as we start to increase beta, now in the second image in the center, we have a positive beta, and you can see now this is an interesting case also because beta 1 plus beta 2 is equal to phi 0, and so we get a linear harmonic function. But as you can see here, we are not yet at the point where we have a 90 degrees angle with the drift. This one is represented in the third image, and this is the point that we want to concentrate at. So we are going to choose beta 1, beta 2 very close to these values, because at these values the drift at the boundary is 0, and we can control what will happen with the sine with just a perturbation on the betas. So the betas will change in the following way. If we take beta 1 less than phi 1 and beta 2 less than phi 2, then with alpha less than 1, h to the alpha is a super martingale. And then the probability that tau a is larger than n, we have the upper bound that is of order n to the of a constant divided by n to the power alpha beta over 2. And the same thing, or analogous, is if we take, now if we're going for the submartingale, we take beta 1 larger than phi 1, beta 2 larger than phi 2, and alpha larger than 1, so that we get a lower bound of order on the return times of order c divided by n to the alpha beta over 2. So you see is they will be slightly off the value when beta 1 equals phi 1, beta 2 equals phi 2, and alpha equals 1. So this would be the point around which we have our almost martingale. And that gives us the chi, which is phi 1 plus phi 2 divided by phi 0, which is the formula in beta, right? We choose beta 1 equals phi 1, beta 2 equals phi 2, and then we perturb this a little bit to get our bounds. And that's how we get the formula for the quantification of the return times of our process. Okay, I hope this has been clear and enjoyable for you. And if you have any questions, please let me know. I will stop here. Thank you.